Tonight, we're going to examine a journey that may look like the next Apollo mission, but could end very differently. When the first humans step onto Mars, the world will celebrate their arrival. Cameras will record the first footprints. Flags will be raised beneath a pale red sky, and somewhere above them, Earth will appear as a tiny point of light, tens of millions of miles away. But landing on Mars will only complete half of the mission. To come home, those astronauts will need another rocket waiting for them on the surface. That rocket may have been sitting alone in the Martian cold for years. Its fuel may need to be manufactured from the atmosphere and ice beneath the ground. Its engines, tanks, computers, power systems, and life support equipment must survive dust, radiation, and enormous temperature changes before anyone presses the launch button. And even if every machine works, the crew cannot leave whenever they choose. Earth and Mars must reach the correct positions in their orbits. Miss that opportunity, and the astronauts may wait more than 2 years for another one. During that time, their bodies will change, their equipment will age, their supplies will shrink. Communication with Earth will arrive minutes late, and no rescue mission will be able to reach them before a crisis is over. The first people on Mars may have a return route drawn into their mission plan, but that does not mean they will ever use it. By the end of tonight, you're going to understand why returning from Mars may be far harder than reaching it. How one failed system could turn an expedition into a permanent settlement, and why the first humans to call Mars home may never stand on Earth again. Before we follow that journey, take a moment to subscribe if you enjoy calm explorations of space, distant worlds, and the engineering that may shape humanity's future. You can also leave a like if this is the kind of story you would like to hear more often. It helps these longer videos reach people who enjoy learning slowly without rushing from one idea to the next. And wherever you are listening tonight, you can settle in, let the room grow quiet, and imagine Earth gradually becoming smaller behind the spacecraft. Because the first journey to Mars will not begin when a boot touches the ground. It will begin years earlier. Before the crew leaves Earth, cargo vehicles may already be traveling toward Mars. One may carry the habitat where the astronauts will sleep, work, eat, exercise, and shelter from radiation. Another may carry a power system. Others may deliver rovers, scientific equipment, food, spare parts, communications hardware, and the machines needed to extract useful materials from the Martian environment. The return vehicle may be sent ahead as well. It could cross interplanetary space without a crew, enter the Martian atmosphere, descend through dust and thin air, and land at a site selected years in advance. Once safely on the surface, it would begin waiting. Engineers on Earth would watch its electrical systems, internal temperatures, battery health, computer status, tank pressures, and communications equipment. They would test what they could from millions of miles away. But no technician could walk around the vehicle with a flashlight. No mechanic could replace a damaged cable or open an access panel. If a hidden defect appeared after landing, the return plan might already be in danger before the astronauts had entered their own spacecraft. This is one of the strange reversals at the center of Mars exploration. On most journeys, travelers bring their way home with them. A ship crosses an ocean and later turns around. An aircraft lands, refuels, and takes off again. Even the Apollo astronauts carried the essential parts of their return system through the entire mission. Mars may require something different. The first crew might leave Earth only after receiving confirmation that a separate collection of machines is already waiting on another planet. Their confidence would depend on sensor readings, test signals, and photographs transmitted across space. Those signals might say that the habitat has power, the communications antennas are working, and the ascent vehicle appears healthy. But appearing healthy is not the same as being guaranteed to work years later. NASA describes human journeys beyond Earth through several connected hazards. The crew must face radiation outside much of Earth's protection. They must live in isolation and confinement. They must operate at enormous distance from medical care and replacement supplies. Their bodies must pass through different gravity environments, and every breath must come from a closed, artificial system surrounded by conditions that cannot support human life. None of these dangers exists alone. Radiation can affect health and electronics. Isolation can affect judgment and cooperation. Distance delays assistance. Reduced gravity changes the body. A closed habitat makes the crew dependent on pumps, filters, sensors, valves, and software operating every hour of every day. The return journey sits at the far end of all those dependencies. For the crew to come home, the astronauts must remain healthy enough to launch. The habitat must keep them alive until the departure date. The power system must continue operating. The return vehicle must survive. Its propellant must be available. Its engines must ignite. Its guidance system must place it into the correct orbit. And another spacecraft may need to meet it above Mars before beginning the long fall back toward Earth. A mission plan can draw this entire route with arrows. The first arrow leaves Earth. The next reaches Mars. Another rises from the surface. The final arrow curves home. On paper, each one appears clean and certain. But every arrow represents machines, fuel, timing, human decisions, and physical limits. And the farther the crew travels, the fewer ways remain to recover when one part of that chain breaks. To understand why Mars changes the rules so completely, we first need to return to the journey that shaped almost every modern expectation of human spaceflight. The journey to the Moon. Apollo gave human spaceflight a familiar shape. A rocket lifted from Florida. Astronauts crossed the distance to the Moon in about 3 days. They landed, completed their work, then began the journey back while the world followed every transmission. The entire route remained close to Earth by interplanetary standards. The average distance between Earth and the Moon is about 384,000 kilometers. Radio signals cross that gap in roughly 1.3 seconds. A message sent from the lunar surface could reach Mission Control in Houston almost immediately, followed by a response after another brief delay. That closeness mattered during every Apollo mission, although its value became clearest in April of 1970. Apollo 13 launched from Kennedy Space Center on April 11th, with Jim Lovell, Jack Swigert, and Fred Haise aboard. Their destination was the Fra Mauro region of the Moon. About 55 hours and 54 minutes after launch, an oxygen tank inside the service module exploded. The crew heard a bang. Warning lights appeared across the control panels. Electrical power began failing as oxygen escaped into space. Jack Swigert contacted Mission Control within seconds. Houston received his voice after the short lunar distance delay. Controllers could already see changing measurements through the spacecraft's telemetry, the stream of technical data transmitted from the vehicle. Tank pressures were falling. Fuel cells were losing their oxygen supply. Electrical readings showed that the command module was rapidly becoming unusable. Hundreds of specialists on Earth began working the problem. Engineers studied wiring diagrams and life support systems. Flight controllers calculated how much electrical power remained. Navigation teams examined routes that could carry the spacecraft around the Moon and back toward Earth. Other teams entered simulators to test procedures before sending them to the crew. This support continued almost continuously for the rest of the mission. The lunar module Aquarius became a temporary lifeboat. It had been designed to support 2 astronauts during a short lunar landing, yet it now had to keep 3 people alive for several days. Carbon dioxide soon became a serious problem. The command module used square filtering canisters, while the lunar module accepted round ones. Engineers on Earth designed an adapter using materials already aboard the spacecraft, including plastic bags, cardboard, hoses, and tape. Mission Control then explained the construction process to the astronauts step by step. The device worked. Apollo 13 splashed down safely in the Pacific Ocean on April 17th, nearly 6 days after launch. Its survival depended on the crew's training and the spacecraft's remaining systems. It also depended on immediate access to a large body of knowledge on Earth. Houston could watch the emergency develop through live data. Specialists could test possible solutions while the crew conserved energy. New procedures reached the spacecraft while they were still useful. A Mars crew would retain contact with Earth. Yet that relationship would work at a much slower pace. A typical journey to Mars using current chemical propulsion would last several months. NASA studies often describe complete missions lasting roughly 2.5 to 3 years, depending on the route and the length of the surface stay. During the outward journey, the spacecraft would move millions of kilometers farther from Earth each day. Any rescue vehicle launched after an emergency began would face its own preparation period, launch window, and months-long flight. Supplies could not arrive during the same week. Replacement hardware could not be delivered during the same month. Medical evacuation would remain unavailable through most of the mission. The experts on Earth would still analyze data and develop procedures. Their knowledge would remain valuable for problems that allowed enough time. Fast emergencies would belong to the crew. A loss of cabin pressure can become critical within minutes. Fire can spread through a sealed spacecraft before a long technical discussion is possible. A serious electrical fault may require switches to be thrown immediately, while the available information remains incomplete. Apollo 13 survived through a partnership between the spacecraft and an entire planet of support. The short distance allowed those 2 groups to behave almost like one team working in the same room. Mars stretches that team across a distance where instructions arrive late and physical assistance cannot arrive at all. The astronauts would carry more training, greater onboard computing power, and procedures designed for independent operation. Even then, a crew of several people could never reproduce every specialty available across NASA centers, universities, hospitals, and aerospace companies on Earth. The old Apollo pattern begins to break at this point. Leaving Mars early may appear to offer protection when conditions deteriorate. Yet departure depends on where Earth will be months later, how much propellant is available, and which path through the solar system the spacecraft can actually follow. The planets set that schedule long before the emergency begins. Earth and Mars are always moving. Earth completes one orbit around the Sun in about 365 days. Mars travels along a wider path and needs about 687 Earth days to complete its own orbit. This means Earth moves around the Sun more quickly, gradually catching Mars, passing it, and then pulling ahead. From a distance, the 2 planets resemble runners circling separate lanes of an enormous track. Their changing positions determine when a spacecraft can travel between them without carrying an impractical amount of propellant. Engineers call a favorable period a launch window. For conventional Mars missions, useful windows return roughly once every 26 months. The spacecraft cannot simply aim toward the red point visible in the sky on launch day. Mars will continue traveling throughout the voyage. During a trip lasting 6 or 7 months, it moves through a large part of its orbit. Navigation teams must aim toward the region of space where Mars will arrive at the same time as the spacecraft. A useful comparison is throwing a ball towards someone who is running. Aiming directly at the runner's current position sends the ball behind them. The throw must lead the target, placing the ball where the runner will be several seconds later. Mars missions use the same basic principle across tens or hundreds of millions of kilometers. Earth also carries the spacecraft around the Sun at nearly 30 kilometers per second before launch. The rocket adds a carefully calculated change in speed, placing the vehicle onto a long curved orbit that crosses the path Mars will occupy months later. One of the most efficient routes is called a Hohmann transfer. It is an elliptical orbit shaped so that one side touches Earth's orbit and the other reaches Mars's orbit. This type of journey saves propellant, although it requires patience and precise timing. The return journey follows the same orbital rules. Earth must be positioned where the returning spacecraft can meet it after months of travel. Leaving too early, too late, or in the wrong direction can require far more energy than the vehicle carries. This is why Mars mission plans often contain long surface stays. NASA's Design Reference Architecture 5, published as a detailed planning study in the late 2000s, used what is called a conjunction class mission. In this architecture, the crew would spend roughly 500 days on Mars. The name comes from the orbital arrangement rather than the surface experience. A conjunction class mission accepts a long stay so the planets can move into positions that allow relatively efficient journeys in both directions. Cargo vehicles would leave during an earlier launch opportunity, about 26 months before the crew. They could deliver habitats, power systems, supplies, and the ascent vehicle that would later lift the astronauts from the surface. After landing, the crew would remain through hundreds of Martian days while Earth continued moving around its orbit. The astronauts might conduct scientific work, maintain equipment, and prepare for departure, yet the return date would remain tied to celestial motion. Other mission studies exchange that long surface stay for different complications. NASA's later Strategic Analysis Cycle 21, usually shortened to SAC-21, examined a much shorter visit. In one studied opportunity centered on the year 2039, 2 astronauts would descend to Mars for about 30 sols, while 2 remained in orbit. A sol is 1 Martian day, lasting about 24 hours and 39 minutes. The entire round trip in that concept would still last roughly 760 to 850 days. More demanding propulsion, additional spacecraft elements, and carefully staged operations would help shorten the surface stay. SAC-21 was a trade study. It explored what a short first visit might require. It was not an approved mission or a fixed NASA schedule. The contrast between these architectures reveals why there is no single duration called a Mars mission. A longer surface stay can reduce some propulsion demands while increasing radiation exposure, equipment wear, consumable requirements, and medical risk. A shorter stay can reduce time on Mars while demanding faster transportation, more complex staging, or greater amounts of propellant. Every design moves risk from one part of the mission to another. For the crew, the calendar would be unlike any calendar used during earlier exploration. A medical problem cannot move Earth forward in its orbit. A damaged habitat cannot create a new low-energy route home. A failing power system cannot make the next launch window arrive sooner. The astronauts may be ready to leave while the solar system is not ready to receive them. And even before they land, the same physics follows them through interplanetary space. Once the spacecraft has entered its transfer orbit, changing direction requires far more than turning the vehicle around. A few hours after the main departure burn, Earth may still look close enough to reach. The planet would remain bright through the spacecraft windows, larger than any star and still recognizably round. Continents might be visible beneath bands of cloud. From inside the cabin, Turning around could feel like a simple matter of rotating the vehicle and firing the engines in the opposite direction. Spaceflight does not work that way. Before departure, the spacecraft and everything aboard it are already moving around the Sun with Earth at nearly 30 kilometers per second. The launch vehicle adds another carefully measured change in velocity, placing the crew onto a new orbit that stretches outward until it meets the path of Mars. That departure maneuver is often called the Trans-Mars injection burn. The word injection describes what the engines are doing. They insert the spacecraft into the interplanetary trajectory that will carry it away from Earth's orbit. Once the burn ends, the vehicle does not coast along a straight line between two fixed planets. It begins circling the Sun along a long ellipse, with Earth moving ahead on its own path and Mars continuing toward the planned meeting point. Every object involved remains in motion. Suppose the crew detects a serious failure one day after departure. The engines could rotate the spacecraft until it faces Earth, yet facing a destination does not create a route to it. The vehicle would still possess the speed and direction established by the original burn. Returning immediately would require cancelling much of that motion, then adding a new change in velocity that places the spacecraft onto an orbit intersecting Earth at the correct time. Engineers describe changes in velocity using the term delta V. Delta is a mathematical symbol meaning change, so delta V simply means a change in speed or direction. Spacecraft carry a limited delta V budget based on their engines, propellant supply, and mission design. A large unplanned maneuver can consume propellant reserved for course corrections, Mars arrival, or Earth return. The tanks cannot be refilled in deep space. Some Mars plans include specific abort options. During an early failure, the crew might use remaining propulsion to adjust the trajectory toward a later meeting with Earth. Other options could send the vehicle around Mars without landing, allowing the planet's gravity to bend its path back toward the inner solar system. These routes would still take months. A free return trajectory is one example. It is designed so that a spacecraft can pass near a planet and eventually return toward its starting region with limited additional propulsion. Apollo 13 used a lunar free return path after the explosion aboard the spacecraft. The Moon's gravity helped curve the vehicle back toward Earth. Mars free return concepts are far longer. Earth and Mars are moving around the Sun on separate orbits, and the spacecraft must arrive where Earth will be when the return path finally reaches its orbit. Depending on when the emergency occurs, the crew could remain in space for a year or longer before approaching home. Later failures offer fewer useful choices. Once Earth has moved far behind, reaching it may require more delta V than the spacecraft can produce. An engine problem could also remove the very capability needed to change course. The crew might then continue toward Mars, because the existing trajectory already leads there. NASA often uses a representative Mars transit of about 6 months when describing future journeys, although some studied routes are shorter and others take considerably longer. Throughout that period, ordinary resupply remains unavailable. A damaged carbon dioxide filter cannot be replaced by a cargo vehicle arriving the following week. A failed computer must be repaired with equipment already aboard. Medical care is limited to the training, medicine, and instruments carried at launch. Even rescue vehicles prepared on Earth would face major delays. Engineers would need to select a suitable rocket, integrate a spacecraft, complete testing, and wait for a trajectory capable of reaching the crew. The rescue craft would then spend months crossing interplanetary space. By the time it arrived, the original emergency would have been over for a very long time. This changes the purpose of every backup system aboard the Mars vehicle. Redundant pumps and duplicate computers are not conveniences. They are replacements already traveling beside the equipment expected to fail. Crew members would train to isolate damaged electrical circuits, stop leaks, manage fires, and keep life support equipment running with reduced capability. Procedures must assume that outside help can provide knowledge while remaining unable to provide hardware. The commitment grows gradually after departure. Earth still appears nearby during the first days, then becomes smaller as the spacecraft follows its widening orbit. The distance may feel visual, yet the true separation is measured by how much propellant a return would require and how long any assistance would need to arrive. The crew must solve immediate problems inside the vehicle carrying them. Experts on Earth can still study telemetry and prepare detailed instructions. Their support remains essential throughout the mission. But as the distance grows, every exchange begins to contain a delay, and that delay eventually changes how the entire spacecraft must be operated. A warning appears on the environmental control panel during the 4th month of the voyage. The carbon dioxide removal system is still working, although one sensor is reporting a slow rise in pressure across a filter bed. The reading may indicate ordinary dust inside the ventilation loop. It could also mean that the material trapping carbon dioxide from the cabin air is becoming clogged earlier than expected. No alarm is sounding. Cabin pressure remains steady. Oxygen levels are normal. The crew gathers the relevant information before contacting Earth. They record the pressure readings, fan speed, cabin temperature, and the times when the sensor began drifting. A short video shows the status lights on the equipment rack. Computer files containing several hours of telemetry are attached to the message. Then the transmission leaves the spacecraft. Radio waves travel at almost 300,000 kilometers per second, the fastest speed allowed by nature. Even at that speed, crossing interplanetary distances takes time. NASA's public mission descriptions commonly place the one-way delay between Earth and Mars at roughly 4 to 24 minutes, depending on where the planets are in their orbits. Technical mission studies often use a maximum near 22 minutes each way. Suppose the crew is currently 18 light minutes from Earth. Their report travels through space for 18 minutes before an antenna on Earth receives it. Mission controllers review the message and route the data to specialists responsible for the life support system. Engineers compare the sensor readings with earlier tests, examine possible failure modes, and prepare a response. That work may take another 20 minutes. Once transmitted, the reply needs 18 more minutes to reach the spacecraft. Nearly an hour may pass between the crew noticing the warning and receiving the first detailed recommendation from Earth. During that hour, the filter pressure might continue rising. A second sensor could begin producing unusual readings. The fan could draw more electrical power as it works against the obstruction. The crew must decide whether the system can safely remain in operation. Waiting preserves the original configuration, allowing engineers on Earth to study clean data. Acting early may prevent a minor restriction from becoming a complete blockage. The astronauts might reduce the fan speed, switch to a backup unit, or open the equipment rack for inspection. Any action changes the situation described in the original message. When Earth's reply finally arrives, it may recommend steps based on readings that are already 40 or 50 minutes old. The crew must compare that advice with the current condition of the system and decide which parts still apply. This is called stale information. The data was accurate when transmitted, yet time has reduced its usefulness. Human spaceflight has traditionally relied on a close partnership between the crew and a large support network on Earth. Flight controllers monitor power, navigation, cabin conditions, and crew health. Specialists who help design individual components can be brought into a discussion. During an emergency, simulators and duplicate equipment Allow engineers to test procedures before astronauts attempt them. That model works well when conversation is nearly immediate. At Mars distance, mission control becomes a source of careful analysis rather than moment-to-moment direction. Ground teams can examine long-term trends, prepare maintenance plans, and study complex problems while the crew sleeps. Immediate decisions remain inside the spacecraft or habitat. The delay shapes ordinary work as much as emergencies. A physician on Mars may transmit an ultrasound scan and wait for a specialist to review it. A geologist may send images of an unusual rock layer, then continue working before receiving advice about which sample to collect. A maintenance request that would take 30 seconds to discuss aboard the International Space Station could require several recorded exchanges spread across hours. Scheduling also changes. The crew cannot request approval for every small adjustment. A delayed rover departure, an unexpected equipment inspection, or a change in weather conditions may require local judgment. Mission plans must provide broad authority instead of depending on constant permission from Earth. Family contact becomes a series of recorded messages. A crew member may describe the day, send the recording, and receive a response much later. At the greatest distances, a simple exchange can require about 44 minutes of signal travel before either person spends time speaking. Research into delayed communication has found increases in frustration and mental workload, along with weaker collaboration during complicated tasks. Mars crews would train for this rhythm and use carefully organized messages, shared databases, onboard expert software, and procedures written for independent action. None of these measures shortens the distance. The crew remains connected to thousands of people working on Earth. Their knowledge continues crossing the gap throughout the mission. Yet, during the few minutes when a pressure leak spreads, an electrical fault develops, or a medical condition suddenly worsens, the astronauts must act with the information already available around them. Months of travel under these conditions eventually bring the spacecraft to Mars, where the most dangerous minutes of the outward journey unfold too quickly for Earth to participate at all. Mars first appears as a growing disk ahead of the spacecraft, its surface still hidden beneath distance and dust. By the time the vehicle reaches the upper atmosphere, it may be moving at several kilometers per second. NASA's Perseverance rover entered the Martian atmosphere in February of 2021 at about 5.3 kilometers per second, close to 19,000 kilometers per hour. Nearly all that speed must disappear before landing. Atmospheric entry begins with a heat shield facing forward. Gas compressed ahead of the spacecraft becomes extremely hot, producing temperatures capable of destroying an unprotected vehicle. The shield absorbs and redirects much of that heat, while the atmosphere begins slowing the craft. Mars creates an unusual problem during this process. Its atmosphere is thick enough to generate dangerous entry heating. Near the surface, however, the pressure is less than 1% of the pressure at sea level on Earth. The thin air cannot provide the amount of drag available to vehicles descending through Earth's much denser atmosphere. A parachute can help, although its usefulness has limits. Perseverance deployed a parachute about 21.5 meters wide, while still moving faster than the speed of sound. The parachute reduced its velocity, but it could not bring the rover close to a safe landing speed. A powered descent stage completed the final part of the journey, hovering above the surface while cables lowered the rover onto the ground. Perseverance had a mass of about 1,025 kilograms. Curiosity, which used a similar sky crane landing in August of 2012, had a mass of about 899 kilograms. These were extraordinary achievements. They also reveal how far human missions must scale beyond previous landings. A crew cannot arrive with only seats, pressure suits, and a small collection of instruments. People need a pressurized habitat, food, water reserves, life support machinery, communications equipment, exercise systems, medical supplies, and protection from radiation. Surface travel requires rovers. Long-term operation requires a dependable power source. Returning to orbit requires an ascent vehicle with engines, tanks, guidance equipment, and propellant. Human Mars studies, therefore, examine payloads measured in tens of metric tons. Some NASA concepts have investigated landers capable of delivering about 20 metric tons at a time. The Strategic Analysis Cycle 21 study used 3 pre-deployed descent systems, with each one carrying roughly 25 metric tons of useful cargo to the surface. That is around 25 times the mass of Perseverance in each landing. A vehicle that heavy carries far more momentum. Momentum describes how difficult it is to stop a moving object and depends on both mass and velocity. Increasing the mass while arriving at a similar speed greatly increases the work required during descent. Conventional parachutes do not scale easily enough to solve the entire problem. A larger parachute creates greater drag, but it must survive enormous forces when opening at supersonic speed. Its fabric, suspension lines, and attachment points all become heavier. Mars still provides too little air for the parachute to slow a very large vehicle to landing speed before the ground arrives. NASA has studied several ways to increase atmospheric braking. One approach uses a lifting body, a vehicle whose shape creates controlled aerodynamic lift during entry. Another uses an inflatable or deployable decelerator, which expands to create a much larger surface area without requiring a rigid heat shield of the same diameter. The final descent may rely on supersonic retropropulsion. This means firing rocket engines while the vehicle is still traveling faster than sound, with the exhaust directed into the oncoming airflow. The engines remove the velocity that the atmosphere and parachutes could not. The timing must be precise. Engines firing too late leave too much speed near the surface. Firing earlier consumes additional propellant, increasing the mass that had to be transported from Earth. A first human mission would probably divide its equipment among several landings rather than place everything inside one enormous vehicle. One landing might deliver the ascent vehicle. Another could carry power equipment and surface transportation. A later vehicle may bring habitat supplies, tools, and spare components. The crew would arrive only after the most important cargo had landed successfully and transmitted confirmation that it remained operational. Location matters almost as much as survival. A habitat landing hundreds of kilometers from the ascent rocket would be of little use to astronauts with limited rover range. Cargo vehicles must reach the same general region while avoiding collisions, dangerous terrain, and debris thrown outward by landing engines. Each descent, therefore, becomes part of one connected surface system. Before the first astronauts are allowed to enter the atmosphere, the equipment intended to keep them alive and eventually lift them away may already have completed the same dangerous journey. And once the ascent vehicle reaches the ground, it begins a much longer test. It waits. Long before the astronauts fasten themselves into their seats on Earth, another launch may already have taken place. That earlier mission would carry no people. Its payload would consist of the equipment the crew expects to find when it reaches Mars, including the machinery needed to leave again. This approach is called pre-deployment. Essential cargo travels during an earlier launch opportunity, lands without a crew, and begins operating before human lives are committed to the journey. NASA's Design Reference Architecture 5 used this sequence. Cargo vehicles would depart approximately 26 months before the astronauts, taking advantage of the previous favorable alignment between Earth and Mars. By the time the crew launched, the first equipment could already have spent many months on the Martian surface. The cargo would be divided according to mass, landing requirements, and mission priority. One vehicle might carry the surface habitat and part of the electrical system. Another could deliver the ascent vehicle that would eventually lift the astronauts into Mars orbit. Additional payloads could include pressurized rovers, scientific instruments, communications antennas, spare parts, and consumable supplies. Some architectures also place an Earth return spacecraft in Mars orbit, where it waits for the surface crew to launch and meet it. A more recent NASA study, known as Strategic Analysis Cycle 21, examined another version of this sequence. That study used 3 pre-deployed descent systems. Each would deliver roughly 25 metric tons of useful cargo to the surface. 2 of the landers would support the return system. Together, they could carry a partially fueled Mars ascent vehicle, additional propellant, surface mobility equipment, and a fission power system. Fission power uses energy released by splitting heavy atomic nuclei, usually uranium. A compact reactor could generate electricity through the Martian night, and during dusty conditions, when solar panels produce less power. The third lander would bring other equipment needed for the short surface mission. Under that studied architecture, 4 astronauts would travel to Mars. 2 would remain in orbit aboard the main habitation spacecraft. The other 2 would descend to the surface for about 30 sols. Keeping half the crew in orbit reduces the amount of equipment that must land and later rise from Mars. The orbital astronauts could also monitor the surface mission, maintain the return habitat, and prepare for rendezvous when their crewmates launched. This remained a trade study rather than an approved mission. NASA uses studies like this to compare possible solutions and identify how one decision changes the rest of the architecture. The central principle is shared by many serious Mars plans. The crew should not leave Earth until the equipment required for survival and return has demonstrated that it reached Mars safely. After landing, each cargo vehicle would begin sending engineering data to Earth. Mission controllers would examine battery voltage, internal temperature, computer health, communications performance, and the condition of any deployable structures. A power system might unfold radiators or connect itself to distribution cables. A rover could drive a short test route and photograph the surrounding terrain. Communications equipment would verify that the landing site could maintain reliable contact with orbiters and Earth. The ascent vehicle would perform its own tests. Its computers could activate backup channels, check sensors, and confirm that heaters were protecting vulnerable components. Tank pressure readings would reveal whether propellant was leaking. Electrical tests could show whether valves and engine control circuits still responded correctly. These checks would continue over months. If a critical system failed, the crew launch could be delayed or cancelled. Another cargo mission might carry a replacement during a later opportunity. The loss would still be expensive, but no astronauts would already be traveling toward a surface they could not safely leave. Pre-deployment, therefore, moves some of the danger into uncrewed missions, where failure can be studied without trapping people. It also creates a strange order of events. The first successful step in a human Mars landing may be the arrival of the rocket that brings the crew away from it. Astronauts on Earth would train while that vehicle sat millions of kilometers away. They might study photographs of its landing site, practice the route between the habitat and launch area, and rehearse procedures using an identical vehicle on Earth. Their final approval to launch could depend on a stream of numbers transmitted from an empty landscape. A healthy battery reading would matter. Stable tank pressure would matter. A successful engine circuit test would matter. Those signals would provide evidence that a return remained possible. Yet the vehicle would still need to survive the crew's outbound voyage, and every day of the surface mission, its seals would experience repeated temperature changes. Dust could settle on exposed hardware. Electronics would continue absorbing radiation. The rocket may arrive first, but its most important task comes much later, after Mars has had years to act upon it. After the cargo lander completes its descent, the ascent vehicle begins the longest quiet period of its mission. No crew climbs aboard. No launch team surrounds it. The vehicle remains on the Martian surface while Earth and Mars continue moving through their orbits. Humanity has landed many spacecraft on Mars, beginning with the Soviet Mars 3 lander in 1971, and followed by missions such as Viking, Pathfinder, Curiosity, and Perseverance. No spacecraft has ever launched from the Martian surface. A human Mars ascent vehicle therefore remains a design concept, supported by engineering studies rather than flight experience. In NASA's Strategic Analysis Cycle 21 study, a partially fueled ascent vehicle would arrive before the astronauts. 2 crew members would eventually use it to leave the surface and rendezvous with the larger habitation spacecraft waiting in Mars orbit. The vehicle's purpose sounds simple when reduced to a diagram. It carries people from the ground into orbit. Inside the machine, that task depends on thousands of individual parts remaining usable after a long period of exposure. On Earth, a launch vehicle is surrounded by technicians until shortly before liftoff. Teams inspect electrical connections, test communication links, and monitor propellant systems. Access platforms allow workers to reach different sections of the rocket. Faulty components can be removed. Replacement parts may arrive from factories hundreds or thousands of kilometers away. Launch delays often occur because an unusual sensor reading, damaged seal, or electrical problem is discovered during these inspections. A rocket on Mars receives none of that support. Its propellant tanks must maintain pressure without developing leaks. Valves must remain closed when commanded and open at the correct moment during launch. Flexible seals must tolerate repeated contraction and expansion as temperatures change. Batteries gradually lose capacity while sitting unused. Heaters must keep critical equipment within acceptable temperature limits without consuming more energy than the power system can provide. Avionics are the electronic systems that control the vehicle. They include computers, navigation equipment, communication hardware, and the circuits that send commands to engines and valves. These systems must remain protected from radiation and temperature changes throughout the waiting period. Wiring creates another long chain of possible failures. A single damaged connection can interrupt power to a sensor or prevent a command from reaching part of the propulsion system. Connectors must remain secure after launch from Earth, interplanetary flight, atmospheric entry, and landing. The engines face their own period of dormancy. Injectors must distribute propellant correctly inside the combustion chamber. Pumps, or pressure systems, must deliver fuel and oxidizer at the required rates. Ignition equipment must function immediately after months or years without use. Guidance sensors must determine the vehicle's orientation and motion. Gyroscopes measure rotation. Accelerometers track changes in velocity. Radar or other navigation instruments may help determine altitude and position during ascent. Each part can work perfectly on the day of landing and still become less reliable over time. Martian atmospheric pressure near the surface is less than 1% of Earth's sea level pressure. The thin air changes how heat moves away from equipment. Dust can settle on exposed surfaces or enter small gaps. Radiation gradually affects electronics and some materials. Daily temperature changes produce thermal cycling. This means the vehicle repeatedly warms and cools as daylight passes over the landing site. Metals, plastics, and composite materials expand slightly when heated and contract when cooled. Thousands of these cycles can place stress on joints, solder connections, and seals. Engineers would design the vehicle to watch itself during this period. Temperature sensors could report conditions inside equipment bays. Pressure sensors would monitor tanks and lines. Electrical tests could measure battery health and resistance through important circuits. The computers might activate backup channels during periodic self-tests. Valves could receive small test commands that confirm their control systems still respond. Guidance instruments could compare readings with known reference values. Some components would be duplicated. Redundant electronics allow a backup computer or communication channel to take over after a failure. Multiple sensors can reveal when one instrument begins drifting away from the others. Every backup increases the vehicle's mass. Extra wiring, protective shielding, duplicate computers, and additional heaters must all be launched from Earth and landed on Mars. Reliability, therefore, becomes a balance between protection and weight. Months later, the crew finally arrives. The astronauts may inspect parts of the ascent vehicle from outside, clean accessible surfaces, and replace components designed for human servicing. Much of the vehicle will remain sealed or difficult to reach. Hidden valves, internal wiring, and engine components must still be trusted based on test results. The waiting period continues throughout the surface mission. A short-stay crew may need the rocket after about 30 sols. A long conjunction-class mission could leave ascent hardware exposed for hundreds of days after the astronauts arrive. Throughout that time, the vehicle must preserve the ability to perform one operation that has never been attempted. Even perfect preservation would solve only the hardware side of departure. The tanks must also contain enough propellant to lift the crew away from Mars, and that propellant may be the heaviest part of the entire return system. The ascent cabin itself may be surprisingly small. It needs enough room for the crew, pressure suits, flight controls, life support, and the equipment required to reach orbit. For a short surface mission with 2 astronauts, the occupied space could resemble a compact spacecraft cabin rather than a complete interplanetary habitat. The cabin is only the payload at the top of a much larger machine. To reach Mars orbit, the ascent vehicle must accelerate until it is traveling several kilometers per second. Mars has about 38% of Earth's surface gravity, which makes departure easier than launching from Earth, though the vehicle still needs a substantial amount of propellant. One NASA reference discussion, connected with the Mars Oxygen In Situ Resource Utilization Experiment, known as MOXIE, estimated that an ascent vehicle carrying 4 astronauts could require roughly 25 metric tons of oxygen and about 7 metric tons of fuel. That gives a total near 32 metric tons of propellant. Most people think of oxygen as something carried for breathing. Inside a rocket, oxygen has a much larger role. Rocket fuel cannot burn in the near vacuum of Mars without an oxidizer, a substance that supplies the oxygen needed for combustion. Earth launch vehicles can draw oxygen from the atmosphere while their engines remain on the ground only in special air-breathing designs. Conventional rockets must carry their oxidizer inside tanks because the atmosphere becomes too thin almost immediately after launch. On Mars, the atmosphere is mostly carbon dioxide and contains very little free oxygen. The ascent vehicle, therefore, needs stored liquid oxygen to burn with a fuel such as methane. Oxygen often accounts for most of the propellant mass. A methane engine may consume several kilograms of oxygen for every kilogram of methane, depending on the mixture selected by the engine designers. The tanks holding those liquids add more mass. Cryogenic propellants must remain extremely cold. Liquid oxygen boils at about -183 degrees Celsius under Earth-like pressure. Liquid methane boils at about -162 degrees Celsius. The tanks require insulation, valves, pressure control equipment, pipes, and structural supports. Engines must be attached beneath them, guidance computers, batteries, landing legs, and a protective outer structure add still more weight. All of this equipment must first reach the Martian surface. A descent vehicle has to carry the ascent rocket through interplanetary space, protect it during atmospheric entry, and slow it during landing. The added cargo makes the descent vehicle heavier, so it needs a larger heat shield, stronger structure, and more landing propellant. That larger Mars lander must then be launched from Earth. The Earth launch vehicle needs enough energy to lift the lander away from the ground and send it toward Mars. Increasing the mass headed to Mars requires additional propellant in the Earth departure stages. Larger propellant loads require larger tanks and stronger structures, which add further mass before the vehicle leaves the launch pad. This compounding effect is one of the central difficulties described by the rocket equation. The equation connects the change in speed a rocket can achieve with the velocity of its exhaust and the ratio between its full mass and empty mass. The exact mathematics can remain with the engineers. Its practical lesson is easy to picture. A rocket carries propellant to move its payload. It must also move the tanks containing that propellant. The vehicle then requires additional propellant to accelerate those tanks. Each new kilogram near the final destination creates extra kilograms during earlier stages of the journey. Returning from Mars causes the mass chain to grow backward. The crew cabin needs ascent propellant. The propellant needs tanks and engines. The complete ascent vehicle needs a Mars lander. That lander needs an interplanetary transport stage and an Earth launch vehicle beneath it. Exact figures vary widely. A vehicle carrying 2 astronauts only to a low Mars orbit would differ from one carrying 4 people to a higher rendezvous point. Engine efficiency, cabin mass, safety reserves, and the orbit of the waiting return spacecraft all change the required propellant. Some architectures bring the ascent propellant from Earth, because doing so reduces dependence on unproven surface machinery. That choice creates a larger landing burden. Other studies attempt to break the multiplying chain by using materials already present on Mars. The planet's atmosphere contains carbon dioxide that can become oxygen through chemical processing. Water ice may provide hydrogen for methane production, as well as additional oxygen. Producing propellant locally could remove tens of metric tons from the cargo that must descend from space. It would replace that transported propellant with compressors, reactors, mining equipment, and a dependable power supply. The return problem would become smaller at launch, while becoming far more industrial after landing. A compact crew cabin could then rise on propellant made from the planet below it. Before that can happen, Mars must support something humanity has never operated beyond Earth: an automated fuel factory. To live off the land on Mars would mean building an automated chemical plant on a frozen desert. The phrase sounds simple because it comes from journeys on Earth, where travelers could gather wood, find water, or grow food in existing soil. Mars offers raw materials in far less convenient forms. Its useful substances are mixed into thin air, locked inside ice, or bound within minerals. The atmosphere provides the easiest starting point. About 95% of Martian air is carbon dioxide. On Earth, carbon dioxide makes up only a small fraction of the atmosphere. On Mars, it surrounds every lander, although the total air pressure near the surface is less than 1% of Earth's sea level pressure. A fuel plant must pull this thin gas through an intake. Compressors then squeeze it into a smaller volume, increasing its pressure enough for chemical processing. Filters remove dust that could damage pumps or contaminate the equipment. One possible system would produce only oxygen. A process called solid oxide electrolysis can split carbon dioxide molecules at high temperature. Each carbon dioxide molecule contains one carbon atom joined to two oxygen atoms. Inside the device, oxygen ions move through a heated ceramic material. The system releases oxygen on one side and carbon monoxide on the other. The oxygen could support breathing, although rocket engines would need far more of it than the crew. Producing methane as well requires another raw material: hydrogen. Mars does not offer large amounts of free hydrogen in its atmosphere. The most practical source may be water ice. Orbital instruments and surface missions have found extensive ice beneath the ground in many regions, especially at higher latitudes. Extracting that water would require drilling, excavation, or heating frozen soil. The released vapor would need to be captured, condensed, and purified. Martian soil contains salts and fine mineral particles that must remain outside sensitive chemical equipment. Once purified, water can pass through electrolysis. Electricity separates each water molecule into hydrogen and oxygen. The hydrogen can then enter a Sabatier reactor. The Sabatier reaction is named after French chemist Paul Sabatier, who studied catalytic hydrogen reactions around the beginning of the 20th century. Inside the reactor, carbon dioxide from the Martian atmosphere combines with hydrogen. A metal catalyst helps the reaction proceed without being consumed by it. The products are methane and water. The methane becomes rocket fuel. The water can be sent through electrolysis again, recovering some of the hydrogen for reuse. This recycling reduces the amount of water that must be extracted, though the full system still experiences losses. At that point, the plant has produced gases. Rocket tanks need dense liquids. Methane must be cooled to about -162 degrees Celsius to become liquid at normal pressure. Oxygen requires a temperature near -183 degrees Celsius. Refrigeration equipment must remove heat continuously. Insulated pipes carry the liquids into storage tanks. Pressure control systems manage any gas produced as small amounts of propellant warm and boil. This gradual evaporation is called boil-off. Even heavily insulated tanks absorb some heat from their surroundings. Over hundreds of days, small losses can become large enough to affect the launch reserve. The complete operation requires much more than a single reactor. Atmospheric compressors draw in carbon dioxide. Mining equipment collects water-bearing material. Purification systems protect the chemistry from dust and salts. Electrolysis units consume electricity. Refrigerators cool the final products, while storage tanks preserve them until launch. Every part depends on power. A failed pump can halt water delivery. A damaged compressor can stop oxygen production. Trouble inside the refrigeration loop may allow finished propellant to escape as gas. Producing fuel locally replaces tens of metric tons of transported liquid with a smaller set of machines. That trade can reduce the mass launched from Earth, provided the machinery works for months before the crew needs it. NASA has examined both approaches. Some studies rely heavily on in situ resource utilization, usually shortened to ISRU, meaning the use of materials found at the destination. Other initial mission concepts carry ascent propellant from Earth to reduce dependence on mining and chemical systems that have never operated at human scale on Mars. Each choice moves the difficulty. Carrying fuel increases launch and landing mass. Manufacturing it creates an industrial chain on a planet without technicians, warehouses, or replacement factories. The chemical reactions themselves are well understood. One small experiment has even produced oxygen directly from the Martian atmosphere. Its results showed that the first step can work. They also revealed the enormous distance between making a few grams of oxygen and filling a human ascent vehicle. That first real test traveled to Mars inside the Perseverance rover. Perseverance landed in Jezero Crater on February 18, 2021. The crater is about 45 kilometers wide, and once held a lake fed by an ancient river. Most of the rover's instruments were built to study rocks, climate, and possible signs of past microbial life. One instrument had a different purpose. The Mars Oxygen In Situ Resource Utilization Experiment was shortened to MOXIE. It was a compact metal box installed inside the rover, roughly the size of a car battery. Its job was to draw in Martian air and prove that useful oxygen could be separated from the carbon dioxide surrounding it. That air is extremely thin. Near the surface, Mars has less than 1% of Earth's sea-level atmospheric pressure. MOXIE, therefore, needed a small compressor to pull the gas inward and squeeze it to a pressure the rest of the instrument could use. A filter kept dust from entering sensitive components. The compressed carbon dioxide then passed into a device called a solid oxide electrolysis stack. Electrolysis uses electricity to separate molecules into different chemical parts. In this case, the system heated a ceramic material to roughly 800 degrees Celsius. At that temperature, oxygen atoms could be removed from carbon dioxide molecules and moved through the ceramic. Pairs of oxygen atoms then joined together to form molecular oxygen, the same form used by human lungs and rocket engines. Carbon monoxide remained as a waste product and was released back into the Martian atmosphere. MOXIE carried sensors that measured the amount and purity of the oxygen before venting it outside. It had no storage tank large enough to preserve the product. The experiment's goal was to test the process rather than collect a useful supply. Over the course of a full Martian year, MOXIE operated 16 times. Those runs took place during different seasons and at different times of day. Engineers wanted to know whether changes in temperature and atmospheric density would affect performance. Martian air becomes slightly thicker during colder periods and thinner when it warms, changing how much carbon dioxide the compressor can collect. Across all 16 runs, MOXIE produced 122 grams of oxygen. That is close to the amount a resting person on Earth might breathe in several hours. The instrument reached a maximum production rate of 12 grams per hour, and the oxygen was at least 98% pure. For a technology demonstration operating on another planet, those results were important. The compressor worked in the thin atmosphere. The heated ceramic survived repeated use. The electrochemical process separated oxygen under real Martian conditions rather than inside an Earth laboratory designed to imitate them. MOXIE also exposed the size of the remaining challenge. A representative human ascent concept may require around 25 metric tons of oxygen. That equals 25,000 kilograms, or 25 million grams. At MOXIE's highest rate of 12 grams per hour, producing that amount would take more than 2 million hours. Continuous operation would extend for nearly 240 years. A human-scale machine would need to work far faster. NASA has estimated that a practical successor may need to produce roughly 2 to 3 kilograms of oxygen every hour. At those rates, accumulating 25 metric tons would still require approximately 1 to 1.5 years of nearly continuous operation. The larger system would also need to liquefy the oxygen. MOXIE released its product as warm gas. Rocket propellant must be cooled into a dense liquid near -183 degrees Celsius, transferred through insulated pipes, and stored without losing too much through gradual evaporation. A crude system would run for months rather than several hours at a time. Filters would need cleaning or replacement. Compressors would experience wear. Heating elements and ceramic cells would complete thousands of operating cycles. Backup equipment would be needed in case one production line stopped. MOXIE demonstrated the chemical heart of the process. It did not mine water, manufacture methane, fill a rocket tank, or maintain cryogenic propellant through a Martian year. Those tasks belong to a much larger industrial network. Still, the 122 grams mattered. Before MOXIE, oxygen production on Mars existed in calculations, laboratory chambers, and mission proposals. After its final run, humanity knew that a machine could inhale Martian air and release oxygen from it on the planet itself. Turning that small breath into a launch supply requires a steady source of electricity operating through cold nights, dusty seasons, and every interruption the surface can produce. A human-scale oxygen plant would draw far more electricity than the compact experiment carried by Perseverance. Power would first reach the atmospheric compressor, which must pull carbon dioxide from air with less than 1% of Earth's sea level pressure. Electricity would heat the electrolysis cells, operate pumps, run control computers, and keep pipes from becoming blocked by extreme cold. The plant would also need to remove waste heat. Every motor, electronic circuit, and chemical reaction produces heat while operating. On Earth, factories can move that heat into rivers, cooling towers, or dense surrounding air. Mars offers only a thin atmosphere, so large radiators may be needed to release heat toward the sky. These flat panels would contain fluid circulating through internal tubes. Warm fluid leaves the machinery, crosses the radiator, and returns at a lower temperature. Damage to a pump or a small leak in the cooling loop could force the entire production system to reduce power or shut down. A dependable electrical source therefore becomes part of the return vehicle. NASA's current studies for initial human Mars missions favor nuclear fission as the primary surface power technology. Fission releases energy by splitting heavy atomic nuclei, usually uranium, inside a controlled reactor. One studied short-stay architecture uses a system producing about 10 kilowatts of electricity. 10 kilowatts is enough to operate several ordinary homes on Earth, although a Mars base would use that supply very carefully. The electricity could support communications, charge rover batteries, maintain equipment temperatures, and preserve the ascent vehicle while it waits. A larger settlement or full propellant factory would require considerably more power. NASA's Fission Surface Power work examines reactors designed to operate continuously for years. Their output would continue through the Martian night and during dusty periods when solar generation falls. Solar arrays may still contribute useful electricity. Mars receives less sunlight than Earth because it orbits farther away. Dust suspended in the atmosphere can reduce the light reaching the ground, while fine particles settling on panels gradually lower their output. The length of daylight also changes with season and latitude. Solar systems would need batteries or another storage method for nighttime operation. Large arrays might require cleaning equipment, replacement sections, and cables running across the landing site. A reactor avoids dependence on sunlight, though it introduces its own machinery. The system needs control equipment, shielding, electrical converters, and radiators. It must be transported from Earth, landed safely, and positioned far enough from the habitat to limit radiation exposure. If the mission plans to manufacture methane, electrical power must also reach the water source. Orbital radar and neutron measurements have revealed widespread subsurface ice on Mars, particularly away from the warmest equatorial regions. A landing site selected for easy access to ice may face colder temperatures or more difficult terrain. Prospecting instruments would first confirm how much water exists beneath the surface. Drills or excavators could then collect frozen material. Heaters would release water vapor, which must be captured and condensed before salts and fine mineral grains are removed. Purified water enters an electrolysis unit, where electricity separates it into hydrogen and oxygen. The hydrogen combines with atmospheric carbon dioxide inside the Sabatier reactor, producing methane and water. At the end of this chain, the plant has created warm gases. Rocket tanks need liquids. Oxygen must be cooled to around -183 degrees Celsius. Methane becomes liquid near -162 degrees Celsius. Refrigeration machinery removes heat in stages until each gas condenses into a much denser fluid. The liquids then travel through insulated pipes into storage tanks. Sensors monitor temperature, pressure, and quantity throughout the filling process. Storage continues for months. Even well-insulated tanks absorb small amounts of heat. Some liquid changes back into gas, raising the pressure inside. This gradual process is called boil-off. The system may vent part of that gas, cool it again, or use advanced insulation to reduce the loss. Every solution consumes power or adds mass. A refrigeration failure could allow valuable oxygen to warm and escape. Trouble in the power system might stop atmospheric collection before the required amount has been produced. A broken mining component could remove the hydrogen supply needed for methane. The return rocket now depends on an electrical network, a chemical plant, and cryogenic storage equipment working together across an empty industrial site. Each system protects the others. Power preserves the propellant. Cooling protects the tanks. Mining supplies the chemistry. Control computers keep the entire process balanced. All of these machines must operate in direct contact with Martian dust, low pressure, temperature swings, and radiation. Mars does not remain outside the factory for long. A single grain of Martian dust may be smaller than the width of a human hair, yet it can still reach places that engineers would prefer to keep sealed. It can settle inside the hinge of a rover panel, cling to the fabric around a suit joint, or ride through an airlock on the surface of a boot. One grain causes little trouble. Thousands of surface operations allow fine material to accumulate across equipment that must remain reliable for months. Mars has enough atmosphere to carry dust over long distances. Near the ground, however, its pressure remains below 1% of Earth's sea level pressure. The thin air cannot carry heat away from machinery efficiently, and it offers little resistance to fine particles once winds lift them from the surface. Dust can settle across a radiator and reduce the rate at which it releases heat. Optical navigation sensors may lose contrast as particles coat their protective windows. Solar arrays produce less electricity when the active surface becomes covered. Seals around hatches and rotating shafts can suffer abrasion as hard mineral grains move through narrow gaps. The astronauts' suits would collect dust during every walk outside. Martian soil contains iron-rich minerals that give the planet its color, along with salts known as perchlorates. Perchlorates contain chlorine and oxygen. In sufficient amounts, they can interfere with thyroid function and create other health concerns through inhalation or contaminated food and water. A suit port could reduce contamination. In this design, the rear of the spacesuit attaches to the outside of the habitat, allowing an astronaut to enter it through a hatch without bringing the entire suit indoors. Even then, gloves, tools, sample containers, and mechanical connections would still cross between the surface and the pressurized living area. Filters would collect part of the material that enters. Air quality sensors would track suspended particles. Floors and work surfaces would need regular cleaning inside a habitat where dust cannot simply be swept through an open door. In July of 2026, NASA established an initial exposure requirement for Martian dust. For scenarios lasting up to 30 days, particles smaller than 10 micrometers must remain below a 24-hour average concentration of 0.1 milligrams per cubic meter. A micrometer is 1/1000th of a millimeter. Particles below 10 micrometers are small enough to enter the respiratory system, making them especially important for air monitoring. The standard remains cautious because no mission has returned an authentic sample of airborne Martian dust to Earth. Rovers have examined soil and rock directly, while meteorites from Mars provide additional chemical evidence. The exact mixture that future crews would inhale after repeated surface work is still uncertain. Dust also changes how power systems behave. In 2018, a planet-encircling storm spread through the Martian atmosphere and sharply reduced the sunlight reaching the ground. The solar-powered Opportunity rover entered a low-power condition as its batteries lost charge. Its final communication reached Earth on June 10th. Engineers continued sending commands for months, but the rover never responded, and NASA declared the mission complete in February of 2019. Opportunity had operated since January of 2004, surviving for more than 14 years after a mission planned for 90 sols. Its ending showed how atmospheric dust can become an electrical problem even when the hardware itself remains intact. A crewed base could use nuclear fission for dependable primary power, but dust would still affect radiators, connectors, external cameras, and moving equipment. Reduced solar output would matter wherever panels supplied backup electricity or charged vehicles away from the reactor. Temperature changes add a slower form of wear. A Martian day lasts about 24 hours and 39 minutes. During each cycle, exposed equipment warms under daylight and cools after evening arrives. Materials expand slightly as they heat and contract as they cool. Repeating this process can fatigue solder joints, loosen electrical connections, and place stress on seals made from materials that respond differently to temperature. Low atmospheric pressure complicates the process because the surrounding air transfers relatively little heat. Machinery depends more heavily on conduction through its structure and radiation from exposed surfaces. A radiator coated with dust may therefore affect several systems sharing the same cooling loop. Mars gradually enters the base through fine particles and repeated mechanical wear driven by temperature changes. The effect builds across every rover trip, maintenance task, and airlock cycle. A 30-sol expedition would experience this environment for about 1 month. A long conjunction-class mission could repeat the same exposure for roughly 500 sols, allowing small losses and hidden damage far more time to accumulate. A long stay on Mars begins to reveal itself through repetition. 500 days is not a fixed requirement for every human mission. It comes from traditional conjunction-class architectures, including NASA's Design Reference Architecture 5. In that approach, the crew accepts an approximately 500-day surface stay, while Earth and Mars move into positions that support a relatively efficient return. A shorter visit is possible under a different design. The Strategic Analysis Cycle 21 study examined a surface mission lasting about 30 sols. 2 astronauts would descend, while 2 remained aboard the orbital habitat. A sol is 1 Martian day, lasting about 24 hours and 39 minutes. So 30 sols would amount to a little more than 31 Earth days. The difference between 30 sols and roughly 500 days changes almost every part of the mission. A short stay demands a transportation system capable of reaching Mars, supporting orbital operations, landing the surface crew, and departing again within a narrow schedule. A long stay allows the planets to move into more favorable geometry, reducing some propulsion demands and giving the crew far more time for exploration. That extra time must be supported hour by hour. 500 surface days contain around 1,500 meals for each astronaut. A crew of 4 would consume about 6,000 individual meals before departure, even before emergency reserves are counted. Exercise would occupy hundreds of sessions. Crew members returning from months of weightlessness would need regular resistance training and cardiovascular work to preserve muscle, bone, and coordination in Mars's weaker gravity. Life support checks would occur every sol. Filters would be inspected. Water processing equipment would be monitored. Carbon dioxide removal systems would cycle repeatedly as the crew breathed inside the sealed habitat. Surface operations would create their own calendar. An astronaut preparing for work outside might spend hours checking the suit, attaching tools, confirming oxygen pressure, and passing through the airlock. After returning, the suit would need inspection for dust, seal damage, and wear around moving joints. A mission containing 2 surface excursions each week could produce more than 140 outings across 500 days. Each excursion would carry dust toward the habitat and add another pressure cycle to the airlock doors, valves, and seals. Rovers would accumulate distance and operating hours. Wheels would cross sharp rocks and loose soil. Batteries would be charged and discharged. Motors, bearings, cameras, and communication equipment would experience repeated thermal cycles. NASA surface operations studies divide each sol into competing needs. The crew must sleep, eat, exercise, maintain the habitat, review plans, complete medical checks, prepare equipment, and communicate with Earth. The hours left for science are whatever remain after the systems protecting the crew have received attention. A long mission provides genuine scientific advantages. Astronauts could travel beyond the immediate landing area, examine layers of rock formed during different periods of Martian history, and drill beneath the radiation-altered surface. Seasonal changes could be observed directly. Instruments could remain deployed long enough to record weather, seismic activity, and the movement of dust across much of a Martian year. The same duration increases exposure throughout the habitat. A water recovery system, losing only a small amount each day, may waste a significant reserve over hundreds of cycles. A battery that slowly loses capacity could begin affecting rover range late in the mission. Minor leaks of air, coolant, or stored gas may remain manageable for weeks and become serious after many months. Radiation dose continues accumulating throughout the stay. Medications age inside storage cabinets. Food loses quality. Replacement filters and lubricants are used one package at a time. Uncommon failures also become more likely as operating hours increase. A component rated for thousands of cycles may approach that number. A backup installed early in the mission might itself be old by departure day. 500 days, therefore, describes far more than the distance between 2 dates. It measures the number of times the habitat must restore safe air, recover water, reject heat, preserve food, and protect equipment from the surface outside. The crew can remain only while those loops continue closing. Among them, the water and air systems perform the most intimate work. The same limited supply must pass through the habitat again and again, cleaned after every use and returned to the crew. The water poured into a breakfast pouch begins another circuit through the habitat. Some of it remains inside the body for hours. Some leaves through urine. A smaller amount escapes through sweat and breathing, entering the cabin air as invisible water vapor. Ventilation carries that humid air through a condensing heat exchanger. As the air cools, water collects on metal surfaces and drains into the recovery system. Urine follows a separate route through equipment designed to remove most of its water while concentrating salts and other waste. The remaining liquid passes through filters that capture particles and chemical contaminants. Catalytic reactors then use heat and oxygen to break down traces of organic material. Sensors measure conductivity and other properties that indicate whether the water is clean enough to drink. Microbial control remains essential throughout the process. Bacteria can grow inside damp pipes, tanks, and filters, forming thin colonies called biofilms. Disinfectants, heat, and regular sampling help prevent those organisms from spreading through the system. After treatment, the recovered water returns to storage. The International Space Station has provided the longest practical test of this kind of recycling. Earlier versions of its equipment recovered roughly 93 to 94% of the water used aboard the station. NASA later added the brine processor assembly. Brine is the concentrated salty liquid left after most water has been removed from urine. The processor extracts additional moisture from this residue, helping the station reach an overall recovery rate of approximately 98%. That improvement matters greatly during a Mars mission. If a crew uses 20 liters of water in a day and recovers 98%, about 4/10 of a liter remains unrecovered. Across 500 days, that small daily difference reaches roughly 200 liters. Actual consumption and recovery would vary, but the principle remains the same. A highly efficient loop still needs stored replacement water or a dependable local source. Air follows another repeating path. Crew members inhale oxygen and exhale carbon dioxide. Machines remove the carbon dioxide before it reaches harmful concentrations. Some systems vent it outside, losing the oxygen atoms contained within it. A more advanced habitat can recover part of that oxygen. One method combines carbon dioxide with hydrogen inside a Sabatier reactor, producing water and methane. Electrolysis can then split the water, returning oxygen to the cabin. NASA targets for deep space habitats have called for at least 98% water recovery and around 75% oxygen recovery from exhaled carbon dioxide. The missing fraction must still come from stored reserves or local production. Every stage depends on ordinary mechanical parts. Pumps move fluids through narrow lines. Membranes separate water from dissolved material. Valves direct flow between tanks and processing units. Sensors tell the computer whether pressure, temperature, and purity remain within safe limits. Filters eventually become saturated. Pump bearings wear. Flexible seals stiffen after repeated temperature changes. Deposits can build inside pipes and reduce flow. On the International Space Station, replacement components can arrive aboard cargo spacecraft. Engineers on Earth can examine failed hardware, manufacture a revised part, and send it during a later resupply mission. Mars crews may have no comparable supply chain. Mission planners must choose spare parts years before the equipment begins operating. Every spare consumes storage volume and launch mass. Carrying a second pump may mean leaving behind scientific equipment, food reserves, or another useful tool. Some components fail frequently enough to justify several replacements. Others are unlikely to break, yet their failure would disable an entire system. Engineers study reliability records and build computer models to estimate which parts deserve space aboard the mission. They may include interchangeable motors, standardized valves, repair kits, and raw material for limited three-dimensional printing. The crew would still face failures nobody predicted. A damaged housing might be patched. A blocked pipe could be bypassed with flexible tubing. Two weakened systems might be combined to create one working unit. This kind of repair demands access. Equipment bays need enough room for gloved hands, tools, and replacement modules. Connections must be labeled clearly. Components buried behind permanent structure may be impossible to reach when they matter most. The habitat gradually becomes a collection of machines supporting one another. Water recovery depends on electrical power and working pumps. Oxygen recovery relies on clean chemical reactors. Temperature control protects the electronics that monitor every loop. The rocket outside may represent the final escape from Mars, but survival until launch depends on equipment that looks far less dramatic. A small pump behind a wall panel can become just as important. Mechanical systems can sometimes be bypassed, rebuilt, or replaced from storage. A serious medical emergency places the same isolation around a far more complicated system: the human body. A dull ache begins in one astronaut's lower jaw during breakfast. At first, it feels like pressure from clenching during sleep. By evening, the gum is swollen, and chewing sends a sharper pain through the tooth. The crew must decide whether the problem can wait, whether treatment should begin immediately, or whether the pain signals an infection spreading beneath the surface. On Earth, a dentist could take detailed X-rays, examine the tooth directly, and perform a procedure with specialized instruments. A Mars crew would work with the equipment already inside the habitat and the medical skills carried by a handful of people. One crewmate might photograph the swelling with a close-focus camera. A portable ultrasound machine could examine nearby soft tissue, although ultrasound is less useful for seeing through teeth and bone. Temperature, heart rate, pain level, and blood markers might help reveal whether an infection is developing. The information would be transmitted to physicians on Earth. During periods of long communication delay, medical specialists could receive the data more than 20 minutes after it was sent. They would study the images, discuss possible causes, and prepare instructions. The response would need another 20 minutes or more to cross the distance back. That delay remains manageable for many slow-developing conditions. A rapidly changing emergency may require treatment before Earth's recommendation arrives. NASA identifies delayed communication, limited resupply, and little or no possibility of medical evacuation as central constraints for human missions to Mars. A spacecraft cannot summon an ambulance, and a crew on the surface may be months away from any possible return route. This does not mean that an ordinary cut or toothache automatically becomes fatal. Most minor problems could still be cleaned, monitored, and treated. The risk rises when the required care exceeds what the crew can provide. A wound can develop an infection that needs a different antibiotic. Abdominal pain could come from trapped gas, a kidney stone, appendicitis, or another condition with similar early symptoms. Chest discomfort might result from a strained muscle, while a cardiac problem would require a very different response. Diagnostic uncertainty becomes part of the danger. Medical equipment must fit within strict limits on mass, power, and storage volume. A compact ultrasound device can serve many purposes. A full computed tomography scanner, which produces detailed cross-sectional images inside the body, would be far too large and power-hungry for an early mission. Surgical capability would also remain limited. The crew could carry sterile tools, wound closure supplies, local anesthetic, and equipment for basic procedures. Major surgery requires controlled ventilation, extensive monitoring, trained assistance, reliable sterilization, and the ability to manage complications afterward. Blood products create another difficulty. Red blood cells and plasma require controlled storage and have limited useful lifetimes. A Mars crew may instead rely on carefully selected emergency supplies, medicines that reduce bleeding, intravenous fluids, and procedures designed to stabilize the patient. Pharmaceuticals must remain effective for years. Heat, radiation, moisture, and time can slowly change medications. Some drugs lose strength, others may break down into compounds that are less predictable. Mission planners therefore study packaging, storage temperatures, shelf life, and which medicines deserve duplicate supplies. Crew selection reflects these constraints. Astronauts would be screened for conditions likely to create problems during a long mission. Dental work would be completed before launch. Medical training would extend beyond ordinary first aid, and at least one crew member might have advanced clinical experience. NASA also studies autonomous diagnosis and decision support systems. Software could guide an examination, compare symptoms with stored medical cases, recommend tests, and help the crew follow a procedure when no specialist is available in real time. Surface activities would be judged partly by the injuries they might create. A steep slope, distant rover route, or heavy drilling task carries a different meaning when evacuation ends at the habitat door. A successful treatment may still require days of observation. Infection can return. Internal bleeding may begin slowly. Reduced mobility can increase the chance of blood clots and weaken the crew's ability to perform maintenance. The human body becomes another system that must be monitored with limited spare capacity. Even when every astronaut remains uninjured, each person continues receiving a different kind of exposure throughout the journey. It arrives without pain or warning, passing through the spacecraft and the body one particle at a time. Beyond Earth's magnetic field, the spacecraft enters an environment where energetic particles pass through the cabin every day. Earth is surrounded by a magnetosphere, a vast region shaped by the planet's magnetic field. It redirects many charged particles before they reach the atmosphere. Astronauts traveling to Mars leave much of that protection behind and spend months in interplanetary space. NASA lists space radiation as one of the 5 major hazards of a human Mars mission. The exposure comes from 2 main sources. Solar energetic particles are released during powerful events on the solar surface. These particles, mostly protons, can reach spacecraft in large numbers over a relatively short period. A strong event may raise radiation levels for hours or days, giving the crew limited time to move into the best shielded part of the vehicle. Mission controllers and onboard instruments would monitor solar activity. When sensors detect a dangerous increase, the astronauts could enter a small shelter surrounded by stored water, food packages, and other supplies. These materials contain large amounts of hydrogen. Hydrogen-rich shielding is useful because its light atomic nuclei can slow charged particles while producing less secondary radiation than some heavier materials. Secondary radiation forms when a fast particle strikes the spacecraft wall and breaks atoms apart. The collision can create additional particles that continue into the cabin. Adding shielding, therefore, requires careful material selection rather than simply surrounding the crew with the densest metal available. The second major source is always present. Galactic cosmic rays arrive from outside the solar system. They include protons along with the nuclei of heavier atoms traveling at extremely high energies. Some have moved through the galaxy for millions of years before crossing a human spacecraft. Their energy makes them difficult to stop with a practical amount of shielding. A thick barrier can reduce part of the exposure, though complete protection would require far more mass than a Mars vehicle could launch. Engineers instead combine structural shielding, water placement, storm shelters, mission timing, and continuous monitoring. Each astronaut would wear a dosimeter. This instrument measures the amount of radiation reaching the body over time. Additional sensors placed around the cabin would show which areas provide the greatest protection. The crew would not feel the particles passing through them. Ionizing radiation carries enough energy to remove electrons from atoms. When this happens inside tissue, it can alter important molecules and damage deoxyribonucleic acid, usually called DNA. Cells may repair the damage correctly, repair it imperfectly, or fail to recover. Most individual particle strikes do not cause a noticeable illness. Risk emerges through probability and accumulation. Researchers study possible links between long-duration exposure and cancer, cardiovascular disease, changes in the central nervous system, and altered immune function. Effects on memory, attention, or performance are also being investigated because even a small decline could matter during complicated operations far from Earth. There is no single radiation dose that applies to every Mars mission. Exposure changes with the length of the transit, solar activity, spacecraft shielding, and the route selected. A 30-Sol surface mission creates a different total from a stay lasting approximately 500 days. Mars provides some protection after landing, although far less than Earth. The planet has no global magnetic field comparable to Earth's. Its atmosphere is also extremely thin, allowing more energetic particles to reach the ground. The planet itself blocks radiation arriving from below the horizon, so surface exposure can be lower than exposure in open interplanetary space. Habitats could be covered with Martian regolith, the loose soil and broken rock across the surface. Water tanks and supply storage might also be arranged around sleeping areas or crew shelters. Building beneath several layers of soil would reduce exposure further, though excavation equipment and construction time would be required. Radiation continues throughout the surface stay. Every rover trip moves astronauts away from the thickest habitat shielding. Every maintenance task outside adds another small amount to the mission total. A solar particle event could force crews to remain indoors until instruments show that conditions have improved. Departure begins the interplanetary exposure again. The ascent vehicle carries the crew into Mars orbit, where they join the return habitat and start the months-long journey toward Earth. Radiation accumulated during the outward transit and surface mission remains part of their lifetime total. Nothing about the process announces itself inside the body. The crew relies on instrument readings, shielding models, and medical probabilities developed from incomplete human data. Meanwhile, another environmental change can be felt with every movement. After months without gravity during transit, the astronauts reach a world where their bodies weigh only about 3/8 as much as they did on Earth. The first steps on Mars would come after months without ordinary weight. During the journey, the crew would float through the spacecraft and secure themselves with handrails, foot loops, and straps. Muscles that normally hold the body upright would receive less work. Bones in the hips and legs would carry almost no body weight. Then the landing begins. The astronauts must monitor displays, operate controls, and respond to motion while gravity gradually returns. Once the vehicle reaches the surface, each person weighs about 3/8 as much as on Earth. An astronaut who weighs 180 pounds on Earth would press on the Martian ground with a force similar to about 68 pounds. The person's mass has not changed, so the body still resists sudden movement and remains capable of carrying substantial momentum. This difference can make motion unfamiliar. A heavy tool may feel easier to support while remaining difficult to stop once it begins swinging. A fall develops more slowly, though a pressurized suit can limit the movements needed to recover balance. NASA studies identify locomotion, spatial orientation, hand-eye coordination, and balance as concerns during transitions between gravity levels. The inner ear contains organs that detect rotation and acceleration. In weightlessness, those signals no longer match the pull that the brain has experienced since childhood. After landing, the nervous system must learn another pattern. Walking may begin with short, careful steps inside the cabin. Crew members would practice bending, turning, and lifting before taking on demanding work outdoors. Rover driving and field geology require accurate depth perception, while the body is still adjusting to a new sense of up and down. Months in microgravity also change the tissues that produce movement. Muscles adapt to the loads placed upon them. When the legs no longer support body weight, fibers in the calves, thighs, and lower back can shrink and lose strength. Daily resistance exercise slows this process by using elastic devices, flywheels, or vacuum cylinders to imitate weightlifting. Exercise has reduced deterioration during long stays aboard the International Space Station, although it has not removed every effect. Bone undergoes continuous remodeling. Old material is broken down while new material is built. Weight-bearing activity helps regulate that balance. In microgravity, bone loss can exceed bone formation, especially in the pelvis and legs. The cardiovascular system changes as well. On Earth, the heart must move blood upward against gravity. In orbit, body fluids shift toward the chest and head. The face may appear slightly fuller, while the legs lose some volume. Over time, the body reduces its total fluid supply because the central circulation initially feels overfilled. Returning to gravity can then produce dizziness and reduced exercise capacity. The heart must again maintain blood flow to the brain while standing, and weakened leg muscles provide less help pumping blood upward. Mars offers more loading than weightlessness, but the amount may still be too small to preserve full Earth conditioning. No human has lived for months in lunar or Martian gravity. The Apollo astronauts experienced the Moon's 1/6 gravity for only a few days, far too briefly to reveal long-term effects. One NASA technical assessment has suggested that gravity below roughly 0.4 times Earth's may be insufficient to maintain complete musculoskeletal and cardiopulmonary conditioning. Mars lies slightly below that level, at about 0.38 g. This remains an engineering and biological inference. Direct evidence from people living on Mars does not yet exist. A long-stay crew would therefore continue exercising throughout the surface mission. Equipment may provide loads greater than natural Martian body weight. Medical checks could track muscle strength, heart performance, bone condition, and balance. These preparations support more than daily exploration. When departure arrives, the astronauts must climb into the ascent vehicle and tolerate acceleration during launch. After reaching orbit, they may perform a difficult docking with the waiting habitat. Their bodies then return to weightlessness for the months-long journey home. Earth creates the largest final transition. Re-entry subjects the crew to increased acceleration before the capsule lands. Once outside, full gravity acts on muscles and bones that may have spent years cycling between weightlessness and partial gravity. Standing, walking, and maintaining blood pressure could require assistance followed by structured rehabilitation. A return vehicle may remain mechanically capable of reaching Earth, while the physical demands upon its passengers continue growing throughout the mission. The astronauts would counter those changes with exercise, medical monitoring, and daily routines designed to preserve an Earth-adapted body on Mars. Their social world would be changing at the same time. During certain periods, even the delayed connection with Earth becomes quieter as the Sun moves between the two planets. During solar conjunction, the connection may weaken further. Solar conjunction occurs when Earth and Mars reach opposite sides of the region around the Sun, placing the bright, active solar environment near the path used by radio signals. Charged particles released from the Sun can disturb those signals, creating errors or making commands difficult to trust. The planets are rarely arranged in a perfectly straight line. The disruption still becomes serious enough that robotic Mars missions commonly pause new commanding for roughly 2 weeks. Orbiters and rovers do not simply switch off during this period. Engineers upload schedules in advance, giving each spacecraft a conservative set of activities it can perform without regular direction from Earth. Complex movements may be delayed. Scientific work may continue at a reduced pace, while stored data waits for clearer communication conditions. A human crew would prepare in a similar way, although their habitat could never enter a passive waiting mode. Mission planners would transmit maintenance schedules, medical guidance, navigation limits, and emergency rules before conjunction begins. The astronauts would receive lists of conditions that require stopping an activity or switching to backup equipment. The exact duration of reduced communication would depend on the mission trajectory, the radio frequencies being used, and how much signal corruption engineers are willing to accept. Some low-rate messages may still pass through, while high-volume data, detailed imagery, or software updates become unreliable. Once normal communication returns, the familiar delay remains. Near the greatest separation between the planets, a message may require about 22 minutes to reach Earth. A reply traveling immediately would need another 22 minutes to return. Human response time stretches the exchange further. Conversation becomes delayed correspondence. A crew member might record a message for a spouse before sleeping. The answer may arrive after breakfast on the following sol, carrying reactions to thoughts that no longer feel recent. News from Earth could be hours or days old by the time it is viewed, depending on transmission priorities and crew schedules. Counseling also changes under these conditions. A private session cannot follow the ordinary rhythm of speaking, listening, and responding. The astronaut may record a detailed account of stress or conflict, then wait while a psychologist reviews it. The eventual response can offer perspective and practical support, though the immediate emotional moment has already passed. Privacy becomes a designed part of survival. Each crew member needs a small personal area with a door or divider, a place where light, sound, and social contact can be reduced. Scheduled private communication protects family relationships. Quiet periods allow the crew to recover from constant proximity. NASA treats isolation and confinement as major hazards because they interact with sleep quality, workload, decision-making, and physical health. A habitat may contain advanced equipment, while offering only a few rooms shared by the same people for hundreds of days. The crew becomes its own immediate society. Disagreements cannot be escaped by going home at the end of a shift. A damaged working relationship may affect maintenance, medical care, or surface safety. Conflict management training, therefore, has an operational purpose. Clear authority, predictable schedules, and agreed procedures reduce uncertainty when fatigue begins shaping behavior. Crew selection must consider how people respond to monotony, limited privacy, delayed support, and changing responsibility. Technical skill remains essential, yet a person who performs brilliantly alone may struggle inside a small group that cannot separate for long. Earth continues to influence nearly every major decision. Specialists analyze data, families send familiar voices and faces, mission planners revise schedules from millions of kilometers away. The crew's immediate reality is still contained within the habitat. Outside the windows, the landscape remains physically present. Inside, the same voices answer without delay. The people on Earth remain emotionally important while becoming less involved in the minute-by-minute shape of each soul. Some astronauts may find that separation peaceful. Others may experience homesickness, irritability, or a narrowing sense of time. Responses would differ between people and across stages of the mission. By the time the return opportunity approaches, the crew has lived through months of delayed conversations, repeated maintenance, and local decision-making. Earth has gradually changed from the place managing the mission into the distant destination the mission hopes to reach. Then the calendar finally arrives at departure. Years of planning narrow into tank pressures, weather readings, engine checks, and one scheduled launch from the Martian surface. Several sols before departure, the ascent vehicle begins a final sequence of checks. The crew and mission controllers review the amount of propellant inside each tank. Temperature and pressure readings must show that the liquids remain within their required ranges. Sensors look for gradual leakage, unexpected gas formation, or signs that insulation has lost performance. In NASA's Strategic Analysis Cycle 21 concept, the initial short-stay mission carries ascent propellant from Earth. It does not depend on surface production before the first crew leaves Mars. That choice reduces reliance on an unproven fuel factory, while requiring more mass to survive atmospheric entry and landing years earlier. Valves receive commands and report their positions. Batteries complete load tests. Guidance computers compare their internal data with measurements from external navigation systems. Engine controllers check electrical paths leading to igniters, valves, and pressure regulators. Communication links are tested between the ascent vehicle, the orbital habitat, and Earth. The cabin life support system must hold pressure and remove carbon dioxide during the hours between boarding and docking. Weather remains part of the launch decision. Mars has thin air, but winds and airborne dust can still affect navigation sensors and visibility near the surface. Atmospheric measurements help engineers predict how the vehicle will move through the first part of ascent. The crew also examines the spacecraft directly. Accessible connectors are inspected for dust or damage. Protective covers are removed from sensors and engine openings. Tools, sample containers, and personal equipment are weighed and secured because every kilogram affects ascent performance. Most minimal mission architectures do not assume that a second ascent vehicle is waiting nearby. A serious fault may delay launch if time remains within the departure plan. A failure that cannot be repaired could prevent the crew from reaching orbit. On launch day, the astronauts close the habitat for the final time and cross the surface toward the vehicle that arrived before them. The rocket may have waited through years of thermal cycles before carrying anyone. Its tanks, wiring, guidance equipment, and engines have been protected for this single operation. Inside the cabin, the two surface astronauts connect their suits to onboard oxygen and communications. They secure themselves into couches shaped to support their bodies during acceleration. The other two crew members are already in Mars orbit aboard the habitation element that will carry all four astronauts home. Ignition begins with carefully timed commands. Propellant flows into the engines. Pressure rises inside the combustion chambers. Hot exhaust expands through the nozzles, producing thrust against the vehicle. The landing platform begins to fall away beneath them. Mars's lower gravity reduces the energy required compared with departure from Earth. The ascent vehicle still needs to gain several kilometers per second of velocity before it can remain in orbit. Some designs may use more than one stage. An empty lower stage can be released after its propellant is consumed, allowing the lighter upper stage to continue accelerating. Other concepts may use a single stage sized for the complete ascent. Guidance computers steer continuously during the climb. Reaching space is only part of the task. The vehicle must enter the correct orbital plane, which is the flat geometric path followed by the waiting habitat. It must also reach a suitable altitude at the right point in the habitat's orbit. A small guidance error can grow into a large separation. Engine underperformance may place the ascent vehicle in an orbit too low to survive, or too distant for its remaining propellant to correct. The Strategic Analysis Cycle 21 reference concept sends the two astronauts toward a rendezvous with the crew habitat in a roughly 5-Sol Mars aggregation orbit. An aggregation orbit is a planned path where separate mission elements gather before the journey continues. The ascent vehicle may spend hours or longer adjusting its path. Radar, optical cameras, and radio navigation help determine the distance and closing speed. Small thrusters gradually align the two spacecraft. Approaching too quickly risks collision. Arriving with too little propellant may leave no safe method for completing the final maneuvers. Docking requires both vehicles to remain healthy. The orbital habitat must maintain attitude control. electrical power, communications, and a pressurized docking system. A degraded return vehicle could leave the surface crew in orbit without a functioning route to Earth. Once the docking mechanisms lock together, pressure checks confirm that the passage between spacecraft is sealed. The returning astronauts can finally enter the habitat and rejoin the crewmates who remained above Mars. They have left the surface. The return journey has only begun. The crew now faces months of weightlessness, continuing radiation exposure, aging life support equipment, and an eventual arrival at a planet whose gravity their bodies have not felt for years. After docking, the crew transfers equipment, closes the ascent vehicle behind them, and prepares the larger habitat to leave Mars orbit. A departure engine burn places the spacecraft onto a new path around the Sun. Earth lies months ahead, along that path, moving toward the point where the returning vehicle is expected to arrive. The Strategic Analysis Cycle 21 study examined complete missions lasting roughly 760 to 850 days. More traditional conjunction-class missions can approach or exceed 3 years when the outbound transit, long surface stay, and return journey are combined. By this stage, nearly every major system has already accumulated extensive use. Fans have circulated cabin air for thousands of hours. Water pumps have completed countless cycles. Filters have trapped material from the crew, their clothing, and the habitat itself. Computers have endured radiation while controlling temperature, navigation, and life support. The astronauts have aged inside the same machinery. Radiation exposure continues between Mars and Earth. Exercise equipment must again provide the mechanical loading that gravity supplied on the surface. Water and oxygen recovery remain essential because no resupply vehicle can reach the crew during transit. Medical care remains limited to the people and equipment aboard. A condition that began on Mars may require continued monitoring throughout the return. Medication supplies are older than they were during the outward journey. Small injuries may heal differently in weightlessness, where body fluids shift toward the chest and head. Communication delay gradually becomes shorter as the spacecraft approaches Earth. Conversations begin to feel more immediate, though the crew still operates independently during time-critical events. Months later, Earth grows from a bright point into a visible world. The returning spacecraft approaches at interplanetary speed. It cannot simply slow beside the planet and descend gently. The vehicle must enter the atmosphere along a carefully selected corridor. An entry angle that is too steep creates excessive heating and deceleration. A shallow path may cause the capsule to skip away from the atmosphere or travel far beyond the intended landing region. The heat shield faces forward, as compressed air forms a layer of extremely hot gas around the capsule. Much of the spacecraft's tremendous kinetic energy becomes heat. The crew experiences increasing force as the atmosphere reduces their velocity. Parachutes may deploy after the capsule reaches denser air and slows sufficiently. The final landing could use water impact, ground contact with shock absorbers, or another recovery method chosen for the vehicle. Recovery teams would already be waiting nearby. Medical personnel would enter soon after the capsule is secured. The astronauts might remain seated or reclined while doctors measure blood pressure, heart rhythm, oxygen level, and neurological function. Standing could be difficult. After months in weightlessness, the cardiovascular system may struggle to keep enough blood flowing to the brain. Balance organs inside the inner ear must readjust to constant downward acceleration. The legs must again support full body weight. NASA studies spatial orientation, locomotion, hand-eye coordination, and cardiovascular adjustment because gravity transitions affect each person differently. Rehabilitation would begin almost immediately. Early sessions may involve supported standing, and careful walking. Strength training would rebuild muscles used less heavily during the mission. Balance exercises would help the brain combine signals from vision, joints, and the inner ear. Bone recovery can take far longer than muscle recovery. Doctors would continue monitoring bone density, vision, cardiovascular health, immune function, and radiation-related risks. Some changes may improve over weeks or months. Others could remain detectable for years. Their severity would depend on mission duration, exercise effectiveness, individual biology, radiation exposure, and the amount of time spent in Martian gravity. Physical return therefore unfolds as a process rather than a single landing. The personal return may be equally gradual. Families have spent years adapting to recorded messages and long absences. Children may be older, parents may have aged. Daily routines have continued without the astronaut's physical presence. The crew has also changed through prolonged autonomy. Its members have made decisions without immediate direction, depended on one another for survival, and lived inside a social world containing only a few people. No outcome is guaranteed. Some relationships may strengthen through the separation. Others may require time to rebuild ordinary closeness. The astronauts can stand on Earth again, while discovering that the life they left has continued moving. Their return spacecraft reverses the journey through space. It cannot reverse accumulated exposure, physical adaptation, or years of separate experience. That consequence changes how permanent settlement is evaluated. When every return requires another ascent rocket, another interplanetary vehicle, and another long period of rehabilitation, remaining on Mars begins to appear as an architecture that some future crews may deliberately choose. A permanent Mars mission changes the meaning of departure before anyone leaves Earth. The phrase, "never come back," can describe several different outcomes. A crew may lose its return capability through equipment failure. Astronauts may reach Earth again, carrying physical and personal changes that remain for years. Future settlers could also leave knowing that their mission has no scheduled journey home. Current NASA architecture studies are centered on returning astronauts safely to Earth. NASA has not approved a formal human Mars program or selected a permanent one-way settlement plan. A one-way proposal begins with an appealing calculation. Remove the ascent journey, and the surface mission may no longer need tens of metric tons of return propellant. Some ascent hardware disappears with it. The architecture may avoid a waiting orbital habitat, rendezvous equipment, months of return transit supplies, and the heat shield needed for entry into Earth's atmosphere. Every kilogram removed from Mars departure also reduces mass earlier in the chain. Smaller surface payloads can require smaller descent systems. Earth launch demands fall as well. This is why permanent settlement can appear simpler in diagrams. The savings apply to transportation. Survival becomes an open-ended responsibility. A round-trip expedition only needs its systems to operate through a defined mission. A settlement must keep producing safe air and clean water with no final return date. Power must remain available through equipment failures and dusty seasons. Food production must expand beyond stored packages brought from Earth. Replacement parts become increasingly important as the original machines age. Early settlers may depend on cargo deliveries for filters, medicines, computer components, tools, and specialized materials. Those shipments would still follow the roughly 26-month rhythm created by planetary motion. A lost cargo vehicle could delay a critical replacement for more than 2 years. Local manufacturing would eventually become necessary. A settlement capable of surviving for generations must learn to process Martian materials into useful metals, glass, plastics, and construction products. Machines would need to repair the machines that support them. Agriculture would require protected growing areas, dependable lighting, nutrient control, and careful management of water. Medical care would also need to grow beyond the compact capability of an expedition. Permanent residents would experience injuries, infections, chronic illnesses, and conditions requiring procedures. Population growth would introduce pregnancy, childbirth, childhood development, and the unknown effects of Martian gravity on bodies that had never lived on Earth. No human data exists for an entire lifetime at 3/8 gravity. A lasting community must also make decisions that cannot wait for Earth. Rules for work, safety, privacy, property, and resource use would shape daily life. Disagreements could affect access to power, habitat space, transportation, or medical supplies. Governance would become another system requiring maintenance as carefully as the equipment outside. One of the best-known public proposals for permanent settlement was Mars One. The organization announced plans to send volunteers on one-way missions and attracted worldwide attention during the 2010s. It never developed the launch vehicles, habitats, life support systems, or funding required to carry out the plan. Its commercial organization entered bankruptcy in 2019. Mars One demonstrated how easily the idea of permanence can be described, and how difficult it is to build the machinery behind it. A credible settlement would need the same systems explored throughout this journey, followed by far greater capacity. Regenerative life support must operate continuously. Radiation protection must become part of the settlement structure. Dust control must preserve both machinery and health. Power production must continue while major components are repaired or replaced. Permanence becomes realistic only when Mars supports more than a stranded crew waiting for cargo. The first people who settle there may still keep emergency ascent capability during the earliest years. Later arrivals could bring larger habitats and equipment intended to remain. With each expansion, more work, memory, and responsibility would gather on the surface. Earth would remain visible in the Martian sky during favorable conditions. From the ground, it would appear as a bright point, sometimes accompanied by the moon through a telescope. Messages from family would still cross the distance. News, music, and familiar voices would continue arriving from the planet where every settler was born. For someone on a permanent mission, that light would no longer mark a destination written into the calendar. The immediate world would be closer. It would exist in the pressure reading inside a habitat wall, the water moving through a recovery loop, and the greenhouse leaves growing beneath artificial light. It would include the people sharing meals, repairing equipment, and preparing the settlement for those who may arrive during the following launch opportunity. The first people on Mars may begin the journey believing that home is the world behind them. Over time, home may become the fragile collection of lights, machines, crops, rooms, and human lives they are keeping alive in front of them.